Most of us picture the electrical grid as a giant continuous pipe. A distant power plant generates electricity, pushes it into the wires, and it flows in a straight, uninterrupted line right into your home. But the US grid runs on alternating current. The voltage and the current aren't flowing in a straight line at all. They are constantly sloshing back and forth, pulsing up and down 60 times every single second. That smooth, synchronized pulsing hits a snag the moment it reaches heavy industrial equipment. Large electric motors rely on massive magnetic fields to spin, and generating those magnetic fields physically delays the current. This graph shows exactly what that delay looks like. The tall curve is the voltage, the electrical pressure of the system. The smaller curve is the current. Because of the magnetic fields in the motor, the current curve is pulled out of sync. They are no longer peaking at the same time. Look at the horizontal gap between the peaks of those two waves. That physical separation creates a background energy movement that engineers call reactive power. It doesn't actually turn the motor or do any tangible physical work, but it is completely essential. Without that reactive power, maintaining the magnetic fields inside the equipment, the real power, the energy that actually spins the motor, cannot be delivered at all. Think of it like filling a water tower. If you carry a full bucket of water up a ladder and dump it in, you've done real work. That's real power. But if you carry an empty bucket up and down the ladder without ever dumping it, you haven't done any net work. That's reactive power. You still had to exert physical effort, and more importantly, you are taking up physical space on the ladder. Inside a transmission wire, reactive power takes up physical capacity, exactly like that person walking up and down the ladder. It creates a higher overall electrical current flowing through the metal, leaving less room for the real power we actually want to sell and use. The farther this high reactive current has to travel, the more friction it encounters. As it pushes across hundreds of miles of high voltage lines, it constantly fights the natural electrical resistance of the wires themselves. Forcing that extra current through the wire causes the voltage pressure to drop. Mathematically, the longer the line and the higher the reactive current, the more severe that voltage drop becomes by the time it reaches its destination. This makes reactive power a terrible traveler. The very act of moving it across long distances actively destroys the voltage pressure you need to keep the grid running. Imagine a city demanding a massive amount of reactive power, and the grid operators try to send it from a distant plant across the state. By the time that current reaches the city limits, the voltage on the line has sagged drastically. To push the required energy through at that lower pressure, the system has to draw even more current. That extra current drags the voltage down further, creating a dangerous feedback loop. Eventually, the system buckles. The grid is trying to serve more physical load than the degraded voltage can support. Engineers call this a voltage collapse, and it results in an immediate blackout. You cannot centrally manage reactive power from hundreds of miles away. The physical laws of alternating current make distance the ultimate enemy of voltage stability. Because distance is so destructive to voltage, grid operators have to abandon the idea of a single, uniform power system. Instead, they manage the grid on a strict, localized, zonal basis. They view the grid as an invisible topography, almost like a mountain range. It's called a voltage profile. Voltage levels constantly dip and rise depending on the specific generation and demand happening in a given neighborhood at that exact instant. A dense cluster of heavy manufacturing plants or a massive data center will actively drag the local voltage down, carving a deep, dangerous valley into that topographical map. To prevent a localized voltage collapse from ripping through the rest of the network, engineers have to fill those specific valleys with reactive power exactly where they occur. They solve this using a localized engineering technique called reactive power compensation. Instead of relying on a distant plant, they install specialized hardware right at the local substations. Devices like load tap-changing transformers mechanically adjust the voltage ratio while the system is actively running under heavy load. They also use shunt capacitors. These devices sit right next to the industrial motors and inject their own electric fields to perfectly cancel out the magnetic phase delays on the spot. They physically prop up the local voltage, so the main grid doesn't have to. By producing and absorbing this reactive power locally, the long-distance transmission lines are completely relieved of that burden. Their internal capacity is freed up to safely transport all the real, usable power the city actually needs. We tend to think of the grid as a seamless web, capable of moving energy across entire continents. But that long-distance journey is only physically possible if we carefully maintain the voltage profile right in our own backyards.